All right, physics reaction video number 69. I think today I literally did a search for physics lecture notes filtered by this week, so this should be fresh. Universal gravitation, exciting.
In section 11.2, I'm going to do some numerical examples involving universal gravitation. The lecture got a little bit long, so I split this into two parts, so I'll do the second part in section 11.3. In section 11.1, I mentioned that gravity is weak, but we typically don't think of gravity being weak. We think of gravity as being the dominant force in our everyday life. But gravity is the weakest force that we know about. Just as an example of the weakness of that force, let's take the example of two 100-kilogram people standing a meter apart. With what force do they attract each other? Because the law of universal gravitation says that all objects, including people, attract all other objects like another person.
Wow, this is such a cool way to approach it. It's so interesting how the gravitational force is such a common force in problems that students work. Hey, well, you've got gravity here; it's sliding you down an incline, or whatever. You're throwing a ball and gravity is affecting it, right? So it's the dominant force that they use in their calculations. Occasionally, we throw in some air resistance, but gravity is usually tough enough to beat that. And eventually, you get to electrical forces. And okay, well, now there's these electrical forces. I guess I can do this kind of work. But what's fascinating about it is that the Earth is stinking huge, right? So this idea that gravity is weak, sure, but another way to say it is that the Earth is incredibly massive. And then when you get to the charged particles, of course, they're basically have no mass at all. So it's just so interesting how it's kind of hard to compare and contrast these things. So I think this particular example, right? It's going to be nothing, right? It's going to be nothing, and they should know that, right? People should know that this is nothing, because wouldn't it be weird if this was detectable? Wouldn't it be weird to walk down the street if this was detectable? So I'm going to make a guess here. This is going to be 10 to the minus. What would be undetectable? Let's see, 1g. So thousandth of a g would be undetectable, so less than a thousandth. But I mean, I've done this calculation before, so I know it's worse than that. But I'll say 10 to the minus 6, a millionth of a g. Well, that would actually be a 10 millionth of a g, I guess. So let's see how it goes.
Person. So the force between two people is given by the law of universal gravitation. The value for g.
So interesting, right? No directionality here, and it's between is indicating what the direction is going to be. I can't remember if he actually said the word attraction. What's so fascinating when you go and you take more advanced courses is this equation starts to look way uglier. So sometimes there's a cube down here because there's an extra r vector over here, or there's an r hat, and you got to explain what the heck r hat is. But when you're just going for magnitude, this is just, easy. GMM over r squared, easy. And so I think that this single word here is handling all the directionality, and probably he said it, or he's going to say it, he probably used the word attracting, right? All the directionality is in the text, and we're just going for the numbers here.
As we mentioned in the last lecture, is 6.67 times 10 to the minus 11th. And then we have mass times mass. Both masses are 100 kilograms, so mass times mass gives you mass squared. And we're going to divide this by the distance between them. We've put them 1 meter apart. And so this works out to be an extremely small force, right about 7 times 10 to the negative 7th newtons. And right. This is right about the weight
cool.
of a grain of sand.
Okay. Oh, that's a cool way to think about it.
So
how can you actually think about how it would feel, right? So if I've got two people standing, you say, well, it's like you're feeling the weight of a grain of sand. But the problem is you're standing here and you're attracted this way. And so the grain of sand, if you were to add the grain of sand to this one, it would be pushing down. So do you think about it like this, like two people maybe laying down, and then this top person getting an extra grain of sand down. That's tough because the Earth's gravity is already doing a whole lot. So um, I think this works because, oh my gosh, put a grain of sand in your hand, you hardly feel it, but that's pushing your hand down. Whereas here we're talking about two people maybe attracted to each other horizontally. But I think it drives home just how weak gravity is. This is super cool.
Two people, normal people, a meter apart, normal distance, attract each other with a force about the weight of a grain of sand. That's extremely weak. It's so weak that typically we do not worry about the force of attraction between everyday objects. We ignore it. It's negligible. We only really notice gravity when at least one of the objects in the pair is very, very large, like a planet or a star.
So I just wanted to pause there and think about how, pandemic affects me. I can't believe how much mental energy I'm spending on this, right? You can't have two people standing 1 meter apart. They got to be 2 meters apart. So put a comment in if that was the first thing you were thinking.
And in our everyday lives, the source of that gravity is Earth. Earth has a very, very
Just a quick pause. Look at this beautiful savings of space. He knew he was going to write in here. He left the space, so he put this document together, right? And as usual, I'd love you to compare and contrast in the comments exactly what he did with, let's say, some formatted equations that he maybe slowly revealed, right? And would you reveal just like every equal sign, kaboom, kaboom. But if you go back and watch him when he wrote this down, he said a lot of really interesting things. He talked about the units a little bit, certainly for these two. Don't remember if he mentioned the units of this. But literally speaking while writing gave us, I think, some extra information. So I actually think this was better than a slow reveal. When he wrote this sentence, I don't know, it's like, okay, I got to wait for him to write it. And he was saying it at the same time, and he was speaking slowly to match his writing speed. So occasionally the sentences are maybe useful to do rapid reveals, and he's got a few extra sentences down here that he basically did that, right? So I think this is just a really, really great mix of those two approaches.
Strong gravitational field. It's important that you understand that gravity is weak, but it's also important that you understand that
Hang on. I think there might have been a cut there. Let's just go back to see if there was a cut. So listen carefully.
Very, very strong gravitational field. It's important that you understand that gravity is weak, but it's also important that you understand that gravity becomes rapidly weaker with the distance between the objects increasing. Ooh. Newton's law says that the force of gravity between two objects is inversely proportional to the square of the distance between them. And we can use this relationship to make some predictions between the relative force between two objects. Let's say that we have two asteroids initially a kilometer apart, and they are attracting each other with a force of 100 newtons. Well, with what force do they attract each other when they're 2 kilometers apart, where the distance has doubled? So if we keep...
Just really quick pause here. So if they're a kilometer apart and have this much force, they must be amazingly massive, right? So the example he just did was about a millionth, 10 to the minus 6. So this is 8 orders of magnitude bigger, but it's also 3 orders of magnitude further away, which makes it 6 orders of magnitude smaller. So these are 14 orders of magnitude more massive. Is that right? Yeah, these are pretty big asteroids. Okay, well, that seems they're big, right? And I guess I should maybe compare that with Earth. So that's already really interesting. I just wanted to comment on this, right? So I've talked a lot about the number 2 and how this 2 here and this 2 here can get students a little bit confused. 2 times 2 is 4, and 2 squared is 4. And so 2, I think, can sometimes get students to think, oh, well, there was an extra, because occasionally there's lots of equations that has an extra 1/2 in here. So I don't know if the number 2 always drives the point home about things being squared, but I love that there's a part B that jumps to a very different number, right? So more than doubling here is going to cause a more than quadrupling or one quartering of the answer. So I love this structure here.
Keep in mind that the force is inversely proportional to the radius squared. Well, then we can say that the ratio of forces, force 2 over 4.
Okay, I'm just going to make a prediction here. I haven't looked ahead. There is a math trick that's going to be done here, right? So he could write 1 over r2 squared over 1 over r1 squared, or he could do r1 squared over r2 squared, right? So they're getting the 1 overs right away. I'll be honest, I think I usually do the second one just because I'm usually in a hurry, right? I'm like, oh, well, it's inverse r2 squared over r1 squared. In a video, of course, you can very carefully say it, but I'm just really curious which way he's going to go. I'm going to bet, just at how he's been pretty thorough, I'm going to guess that he's going to do 1 over, 1 over, and then flip it. Let's see.
Force 1 is equal to the ratio of the distances, r2 over r1 squared and inversed.
Whoa! Did not see that coming. Okay. Wow, this is a cool way to do it. So knowing that a ratio is in there, knowing that there's going to be a an R ratio. Oh, this is such a cool way to do it. Jump into the formula. Anywhere there's a thing, do 2 over 1. So do a 2 over 1 there. Go in here, do a 2 over 1 there. And, well, it says to square it. So, oh my gosh. You guys are laughing at me because I never thought about doing it this way. Love it. God, this is so cool. I really like that. So, yeah, say it again. If you've got a formula and you're doing these ratio businesses, go to every single thing and do 2 over 1. Do it there, do it there, but realize you're going to need these parentheses. Oh, man, that was cool.
And we can re-express this as r1 over r2 squared. Cool. So notice that when you take an inverse, you reverse the subscripts. Cool. And we have to reflect the fact that it is inversely proportional.
The other super cool thing is, of course, this scary looking symbol has been replaced with things that students feel much more comfortable with. And that is really the super cool way of doing ratios, right? It turned this proportional to straight equal signs. So that's a really important point.
To r squared. And when you do this, we can put in numbers and calculate rather quickly. So F2, the original force was 100 newtons. The original distance, R1, was 1 kilometer. And the new distance is 2 kilometers.
Oh, and you don't even need to change the units. That's awesome.
Units of kilometers are going to cancel out. And I'd like to point out that right here, that is equal to 1/4. When we double the distance, we are going to 2 squared is 4. So we're going to reduce, right, 1 over the that factor, that ratio squared.
So I'm looking ahead here. So there's a really interesting sort of combination of numbers. So this is going to go down to 25, right? So this is going to become 25. This one is going to go to 4. Sorry, I'm just thinking out loud here. So 1/25th, dividing something by 25 is the same as multiplying something by 4. Right? So you got the number 4 in part A. You're going to get the number 4 in part B. So there's this really interesting symmetry between the two, and it's because 2 times 5 is 10, right? These are, I don't know what those are called. They're a product pair that leads to 10, right? So basically 1 over 2 has a 5 in it. 1 over 5 has a 2 in it. It just depends where you put the decimal place. So these are actually really interesting choices. I'm wondering about opportunities for confusion, right? So the students doing this, will have written a 4 down, In part B, they're going to write a 4 down. Obviously, this is going to be in the numerator. This one's this one's in the denominator. This one's in the numerator. But the 4 kept showing up because of the particular choice of these two things. So I guess I'd love to hear from you guys. Like, how do you pick numbers to do these sorts of things? And do you celebrate interesting coincidences like that? Do you try to avoid them? I don't know. It just got me thinking.
Which gives us 1/4. And 1/4 of 100 is 25 newtons.
And 25 is going to show up.
Okay, well, what if we go to 5 kilometers apart? So if you can reason this out like we did before, doubling the distance quarters the force. Well, what if we multiply by 5? 5 squared is 25. We are then going to reduce the force by a factor of 25. Or if we do it the long way, we can say F2 over F1, which was 100 newtons, is the original distance, 1 kilometer, over 5 kilometers.
Did you see that? Watch this again. Watch how he does the right-hand side.
Over F1, which was 100 newtons, is...
That was so cool. Parentheses, knowing that he's going to have an exponent somewhere, and drawing in the fraction line right away. That's really, really interesting, right? Because it's really driving home we're about to do a ratio here. The parentheses, frankly, is driving home that we're going to raise something to a power. I really like that. I don't think I ever write fractions that way. I always write the numerator, then I write the line, then I write the denominator. But by drawing the line first, it feels like you're really setting up the fact that it's a ratio. That's really interesting.
The original distance, 1 kilometer, over 5 kilometers squared. Inside here we have 1/5 squared. 1/5 squared is 1/25th. And 1/25th of 100 is 4 newtons. So you should really take a second to appreciate this, that if we were to graph the force versus the distance,
Nice.
we would end up getting not just a regular inverse curve like that, it would drop off much more rapidly. And so
cool.
as we get really far from objects, the force between them gets very small very quickly. So when we consider objects that are very far apart, we can consider the force between them to be negligible. And that's why we don't typically worry about the force of gravity from very distant stars, from galaxies that are billions of light years away. We say that those gravitational forces are so small, it's like they're zero.
Very, very cool. I'm probably going to pause here. This was fascinating, right? Like, I'm not sure I'm not sure what level of, I don't know, mathematical exposure you need to be able to look at an inverse graph and then look at a 1 over r squared graph and say, oh boy, those really are different. I had never really appreciated that before, so I loved it. And I'm guessing it's because he really drives home this one in some of his other work. So that's really, really fascinating. I wonder about things like log scales, right? Like a lot of sort of engineering type folks would put this on a log scale and say, wow, whoof, look at that. It's going down at a much steeper slope, right? But I don't think that our students typically have that sort of intuition with the log scales. All right, so just again, I want to point out these really interesting coincidences. Here's a 4, here's a 4, here's a 25, here's a 25. I'm stuck on it, and maybe I shouldn't be, so I'd love to hear your thoughts about it. Wow, whew, man, there was some good stuff in here. Oh man, there was just so many really interesting things. The work that he did on the description of just how weak it is, this really, really cool way of doing the ratios, the way that he drew the fraction here, just super, super awesome stuff. Driving home just how weak it is, especially the further you get away. Man, that was really great. All right, well, hey, everybody, have a great day. And remember, physics teachers are awesome.